Thanks, Sasha. I would like to thank the organizers for inviting me, put together this wonderful conference. It's also the first time I speak with something that is reading up what I say, so it's going to test with the heavy Italian accent, how it goes. So I'm going to talk about a recent paper, appeared in July with my wonderful collaborators, James Drummond, Paul Eslop, and the students of James, Ross, the former student Inek, and then Michele. So mainly the talk is going to be loop correction and string correction in AdS5xS5 when you go away from the gravity approximation. Differently from Shai, I'm going to include the sphere, so it's a nice fact that I will complement what he told before with this last talk. I didn't know about that. But it's important to say that this last paper draws a lot of experience from my previous work, which I listed here. And also a paper that I wrote with Pedro Vieira some time ago. So the plan for today is to give you a brief historical summary and motivations to set up the notations, since many of you might not be familiar with what I'm going to say. And then I'm going to specialize to n equal 4 superior Mills with the motivation of studying quantum gravity correction in AdS5xS5. So the plan would be to study more detailed 4.3 level amplitude in supergravity, then add the alpha prime correction to Virasoro Shapiro amplitudes, then go into one loop in supergravity, and finally explain how it works when you are at one loop and you also have alpha prime corrections. And I will conclude with some conclusions and outlook. In particular, the outlook, I will mention what can be done in different dimensions, different than 4, so for other theories that are not n equal 4 superior Mills. So a brief historical summary that mainly draw from these papers that I read and I like a lot. So some of the papers were born here in KITP, so this one with Polczynski, then this one with Joao also has the affiliation. So the basic starting point is some formalism that was first put forward by Mack. He was thinking about resonant modems in 2-to-2 scattering, and then realized that it's a nice object when you want to study a 4-point correlator to transform it in Mellin space, and the transform is done by factoring out some gamma functions. What is left is some Mellin amplitude I'm calling calligraphic M, and that object is essentially behaves as a scattering amplitude, so it has simple poles at the location of the. At the time Mack thought about this, it was having immense resonances, so I call it M square O for the resonances. Then there's actually some infinite series of poles that goes with M square plus some integer. It has also nice factorization properties, so in many ways this is quite close to a scattering amplitude. Actually, for holographic correlators, the observation is very precise. So what happens is that when you, it's a formula that was also mentioned by Shai and goes back to the work of Joao. When you take these Mellin variables to be very large, then there is a precise formula that tells you that this Mellin amplitude calligraphic M, it's some transform of the actual scattering amplitude in flat space. So this is great because for holographic correlator, the measured plan would be to go ahead and try to study the quantum gravity expansion in AdS5xS5, because these are computed by Witten diagrams. But if you recall how AdS50 works, in front of the supergravity, actually you have n to some power. So when you go away from the free limit, that's a 1/n expansion, so in a G-Newton expansion, so you get knowledge about quantum gravity in AdS. And you can also add an expansion in the tooth coupling, and that's measured by alpha prime higher curvature correction that Shai also mentioned. This is generic in any dimension, even though some theories might have a bigger modular space, so alpha prime is not just the one direction you can explore. And when suppose you succeed in this plan of computing Witten diagrams for arbitrary 1/n expansion, so the kind of question you would like to ask is how the amplitude looks when you go away from the flat space limit, how is the structure, how is it gonna work in details? Can I systematize the 1/n expansion somehow? One might try to understand whether are the emergent symmetries that systematize the expansion, what are the convergence properties, all kind of questions. Then there are most of it that belong to the gravity understanding of the amplitude. And then there are all sorts of questions that have to do with the CFT interpretation. So how the CFT builds the answer, is it complete? How the CFT resolve the divergences, because the quantum gravity expansions might be divergent, individual diagrams might be divergent. But since it comes from string theory, then string theory is finite, so how does it work? And the point of answering all these questions in the modern approach is just not do the diagrammatic computation, but rather bootstrap the result from the CFT using symmetries and some initial knowledge that you need to acquire from the initial data. So the actual the actual title of this talk would have been rather loops and strings and S5 from CFT. But when I first sent it to Sasha, then he replied, thanks a lot, so I didn't want to change with the from CFT, but that's a more proper title. So I'm going to focus first in n equal 4 superior Mills, because something needs to be done compared to the old-fashioned work by Mac and then the formally put forward by Joao. We'll need some generalization, and it's clear why. So we are not just studying some random, some basic CFT with fundamental fields, but the fields we will put as external insertion are alpha BPS KK modes on the sphere. So one is to be a little bit more precise what their dual is in the CFT. And actually it turns out that they are defined, I will define for you single particle operators to be those half BPS state in this, operators in the CFT that are orthogonal to any multitrace you can construct in the CFT. So essentially single particle starts as a single trace, but then it has all sorts of multitraces mixture as you increase the charge, which is going to be denoted by P. And of course, in the OPE, you're inserting scalars from the bosonic point of view, so you just get symmetric traceless representation labeled by twist and spin, but you also have supersymmetry, so these representations are going to be labeled by some SU4 representation, and those are labeled by ABA. And you can think of B as a twist, dual twist for the sphere, and A as a dual spin for the sphere. And this is something that you also need to take into account in the formalism of Mellin space. And then supersymmetry also comes and tells you that the correlator you have studied can be put into free theory plus satisfy a partial normalization theory, so they can be put into free theory plus some kinematics that I'm not going to specify, and then some actual amplitude, which I'm denoting like this, which truly genuinely depends on 1/n and depends on the 2 coupling. So the first generalization I'm going to do about Mellin space is to put the sphere into the game. And I will just do it by taking what was done before. So this kernel of gamma function is the same as the one of Mach. And then I'm going to add some other gamma function that are dual to those. And altogether, the variable I'm using are S-at for the conformal part and S-check for the sphere part. This satisfies some constraints. And then in the end, there are only 2 variables to be that are independent for the conformal part. And for the sphere part, this sum is actually finite, because if you look at this gamma function in the denominator, they give you non-vanishing contribution only in a triangle when you solve this constraint. So this is going to be my kernel to start with, and then do the Mellin transform of these amplitudes on the left-hand side. And what about the flat space limit now? So the flat space limit is something that Joao thought about at the beginning of this story as a bulk point limit. Here we have the sphere, so for the sphere it doesn't really make sense to think about the bulk. So another way to think about it is to think of large external dimensions, so pi, and scale them with a global parameter p times some fixed number, and take p very large. So what it does this in practice is you can look from the gamma function that we used to define the kernel for the Mellin transform. This gives you some classical action. And it turns out that this classical action is the same as the action of 4 geodesics shooting from AdS times S and meeting at a point, whose action, on the other hand, is simply this. So you solve this saddle point, and what happens when you solve this saddle point, you get some solution in which what are the Mellin variables now depend on these cross ratios here, but they depend in such a way that they actually put together the one for the conformal part with the one of the sphere part, so that when you sum them up together in this fashion, they sum to 0. So we started from something that was AdS times sphere-like, but upon doing this saddle point computation, we ended up with something that smells a lot like flat space. But notice that since we have this geometric picture, we can look at the meeting point and compute the momenta of those geodesics. And in fact, this gives a precise way in which the saddle point now is the saddle point of a 10D flat space amplitude, because when you look at these momenta and you put them together, you actually find 10D momenta for a massless particle. And so the generalization of Joao limit to this case is simply this. When you scale the Mellin variables for both the conformal part and the sphere to be large together with the external charges, then the result should be the flat space amplitude in 10 dimensions, in which all the details of this complication, just all the independent dependence on the Mellin variables, both for the conformal part and the sphere part, they just go together in this combination, and these are the flat dimensional Mandelstam variables. And after you've done that, this is quite this statement will be quite important later on, because we will see that this dependence here might or might not be generic. So this is quite we will see that this is quite non-trivial. So the plan for today is to walk you a little bit through the supergravity 3-level amplitude in AdS5xS5, then tell you what you can do once you have this 3-level amplitude, then explain a little bit what happens with the perturbative expansion in which you have the alpha prime correction, and then go into pure supergravity and one loop alpha prime. And then I will just tell you a formula for this one loop alpha prime for generic external charges P1, P2, P3, P4. And there is where you can ask all the interesting questions I posed at the beginning. What's the structure, how it works, the detail, and so on and so forth. So the 3-level supergravity is something that started long time ago. It's not a result I derived, but what I will show you is how it looks like in this formalism of the Mellin amplitude written in this fashion. So it started a long time ago with very heroic computations, and then culminated in this paper of 2016 of Leonardo, where he found a formula for arbitrary external charges, and culminated even more with this other paper of Simoni, which he found a very nice way to rewrite everything. So when you use this Mellin space formalism for both AdS and the sphere, the supergravity amplitude looks as follows. It's super simple. And you get this, the gamma function for AdS times S are precisely this one that I wrote previously here. And then the amplitude is the closest thing you could have think to the actual 10-dimensional flat space amplitude. It's just deformed by this one. And so in fact, what happens when you think about the large P limit is that you just need to drop the one, and that you recover the flat space amplitude. Actually, notice that you could have expected that depends generically on this S check and S hat, or T check and T hat, but it doesn't. So it only depends on these bold variables that are nicely related to 10-dimensional Mandelstam invariance, and it's charge independent. So it doesn't depend on P1, P2, P3, P4, apart from the details of when you take the sums here. So in fact, this function is secretly over-constrained, so it's not an accident. It turns out to be like this, and it's constrained by a symmetry that's Simon found. It's a 10-dimensional conformal symmetry. Note that this is very different from what happens in perturbation theory. So here I told you that there is a saddle point coming from these AdS5 times S5 gamma functions. But when you write perturbation theory with this formalism, the result is essentially this. So you see that in practice there is no amplitude, but everything is gamma function, and the gamma function are function of the Boltzmann variable rather than the individual S hat, T hat, S check, T check. And in fact, you can go on and try to find the saddle point here, and you find no saddle point. You shouldn't find a saddle point, right? Because you are in perturbation theory. Gravity there is non-geometric at least. So you shouldn't be able to find a saddle point of geodesic shooting and meeting somewhere. Now, what you can do with once you have this amplitude under your control is that you can study the spectrum, and the supergravity spectrum here consists of single particles and multi-particles, no stringy states. And the lightest bound states are two particles. These are non-protected operators, so they are long from the point of view of supersymmetry. And they have anomalous dimension of the 1 over n square and 3-point function of order 1. However, the complication when you want to extract the CFT data of these two particle operators is that they are degenerate. So you cannot just go to individual correlators and find their 3-point function and anomalous dimension. You need to do a little bit more involved analysis, but the analysis is quite nice because if you count for given quantum numbers, there are as many anomalous dimension and 3-point function, as many correlators that you can write down for disconnected free theory and 3-level supergravities. So by the punchline is that by putting together not just one correlator but many correlators together, you can gather a lot of information about these two. You can gather enough information about these two particle operators such that you reduce yourself to solve some eigenvalue problems, of which the eigenvalues are the anomalous dimension and the eigenvectors are the 3-point function. So you might wonder from the point of view of the Mellin space where all these particle operators sit, and they sit into the double poles of the gamma functions here that I'm not writing, but essentially from double poles of the gamma function you get some logs that you associate naturally to anomalous dimensions. So I'm not really paying justice to all the story of how the CFT data is extracted from 3-level supergravity, because I tried many times and I always failed. So I'm the last one giving the talk today, so I decided not to insist on this thing, but it's a very cool story. The punchline again is that once you have the 3-point function and the anomalous dimension, then you can use it to learn something about one loop data or higher loop data, just by sandwiching the 3-point function with the anomalous dimension to the right power. And then it's part of the bootstrap story to understand what's the completion of this maximal log. Sorry, here I forgot some log to log of the sum cross ratio. But it's part of the bootstrap story how to complete this maximal log into an actual correlator. I should also say that there are straightforward ways to compute these maximal logs in which you don't just sandwich by hand the 3-point function like you were doing at pizza, but there is some master formula for the lightest correlator you can consider, and then you get all the ones with different charges by applying some simple differential operator. And this story also comes from the 10-dimensional symmetry that Simon found out for the first time. So now that we understood the 3-level supergravity, let me have the alpha prime corrections. So again here, a bunch of papers that discuss this. Again here, differently from supergravity, there were going to be two kind of constraints. The first one is this large P limit in which we know the flat space. And then one will have to again try to complete this large P limit or flat space limit by something that makes the Mellin amplitude an actual correlator. So from the bootstrap point of view, here the completion is done by imposing that the operator you exchange, they have spin, 10-dimensional spin less than equal to n if you're doing some alpha prime to the n plus 3 expansion. It again goes into something like here that I insisted many times explaining, but I always failed, so I will just flash it. If you want to learn more, I can discuss you in private. But let me show you how it looks like when you do all this work and you find the completion. It's always good to get rid of some kinematic hypocammers, so you introduce again something that looks like a transform with gamma functions, and precisely with the hope of getting rid of these hypocammers. So from M you go to some n tilde. But after you've done this, you see that the m tilde actually looks like something that you're used to from the usual Virasoro-Shapiro expansion, plus some other stuff. So there are two kinds of stuff that comes here. Some stuff with arbitrary coefficient B1 and B2 that the bootstrap was not able to fix. But also some other stuff that is fixed and then it's not as leading as the flat space limit here. So there are two sources of completion. One completion is ambiguous, so the bootstrap doesn't tell you what are these coefficients. Another completion looks to be fixed, so what's the criteria to fix all of this? Because if you look at the actual formula, they look like simple, but okay, what's determined is 8, this 9, this 1/2. So the answer for this was found in a beautiful paper by Oleslop, which came out the same day as our paper. So all these complications here, they're just to a covariantization of the flat space Virasoro-Shapiro amplitude when you write it in effective field theory formalism. So you expand it essentially some field phi in derivatives. And the derivative here is taken to be on AdS times the sphere. So it's not just a flat space derivative, but it's actually the covariant derivative on projective space where you have the AdS part and the S part. And so the important thing is that these derivatives don't commute differently from flat space. And this non-commutativity is what generates all this fixed completion here. And instead, the ambiguities that are not fixed by the bootstrap problem for two particle, they come because what you can add to each higher derivative term is some coupling that starts as in flat space, but then since you have the radius of AdS you can play with, you can add lower derivative term will come with the L square. So for example, the ambiguity of the d square phi square term here is just, as I wrote it here, is just the 3-level amplitude, sorry, the phi to the 4 correction, in which here you add some alpha prime square divided L square, for example. Now, before we move to how the loop case works, let me make some comments. The comments are the following. At 3 level, you might think that this is quite good, so the structure is quite rigid. But after a little bit, if you think how these Mellin amplitudes they behave from the point of view of position space, they correspond to some way-2 function by definition of 3 level. So can it be that this is too simple? In other words, the Mellin amplitude here is the only irreducible information because this kernel gamma function gives you the way-2 to start with. So the only thing that you can add by construction at 3 level is some rational polynomial Mellin amplitude. And also based on the OP, when you go away from 3 level, you expect the one loop physics to be generic. So for example, this symmetry that was amazing here, that it's amazing to see here in supergravity should be broken. What's the pattern of this breaking? How do we see it? So to let you understand that there is something special going on here, consider that this kernel gamma function, for example, just depends on the sums of pairs of external dimensions. So it does depend individually on the dimension. So for example, if your Mellin amplitude does not depend on the p's, as it was the case at 3 level, a correlator for which P1 plus P2 is equal to P3 plus P4 is the same, regardless of the values of P1 and P2 and P3 and P4. So the first way you would think to look for how the the tree-level extraction is modified and the one loop feature come into is just pure supergravity with the sphere, of course. But pure supergravity has a structure that we understand, so it's based on some weight for function, weight recompletion, and the bootstrap. And one can nicely see that it goes into the 10D box that is predicted both by string theory and by supergravity in 10 dimensions. On the other hand, the knowledge of this coefficient here, this W4, W3, W2, is quite complicated. And the complication is that from the point of view of the P, they have to support infinite spin, because these two particle operator that I was talking about, they exist for any value of the spin. So for any value of dl that you insert, you have the two particle operators. So from the point of view of the P, you have infinite spin support. So this makes this function W4, W3, and W2, when you look at them in example, for example, 2, 2, 2, 2, 3, 3, 3, and so on and so forth, quite complicated to understand what's the pattern, how to find some structure. They just come out to be some complicated polynomials. So one way we thought about how to solve this issue is to go instead of one loop, but alpha prime cube. And the point is that alpha prime cube can only see as it happens for the flat space amplitude, that when you decompose it into Gegenbauer polynomial contributes to spin 0. Here it happens the same. When you decompose the alpha prime cube amplitude at tree level, it only contributes at 10D spin 0. So when you do the one loop case, you need to essentially square the tree level data with the supergravity, and that propagates this truncation in spin even at one loop. So you expect that the one loop data is going to be quite simpler. In particular, the shape of these function W's that decorate all the various kernels for the transform. And in fact, this is what happens. So for example, W3 here that comes with this polygram of minus S and gives you the log square U, which is fixed by this argument from the two particle data, is simply one line, more or less. Here, this is just some symmetrization that I didn't write. And then the point of the bootstrap is that one has to find the completion of this maximal log. And so we will look at how these calligraphic R and calligraphic B look like. So again, there is, if you look more closely how the OP works, it doesn't just predict the log square U, so this is fully fixed, but it also predicts parts of this function here. And this function will contribute to the log U at one loop. And the important things to understand here is that since we are using this Boltzmann variable, which in a sense are flat space variable, to enter into the transcendental functions here, this function here will cascade when I do the OP decomposition into a contribution. For example, looking at the log U, will cascade to a contribution to log U that is also can also get a contribution from here. So in a sense, there is a fine mixing between this term and these other two terms here when I actually look at the block decomposition. And so you can think of these terms as being some sort of a reminder compared to this term, which is just fixed by the two particle OP data. But when you look at how these remind, so here I'm just considering two instead of one because of the way they come from the point of view of the P. So this is a notation we introduced, but I will not explain. So when you look at how these calligraphic R look like, for example, so it has to, so if the maximal log square U is just given by this, and this by cascading contributes to the log U, this has to be some simple poles. Again, in this both, but the simple poles, quite miraculous, they just come into finitely many number of them, so 6 here, and they are all labeled by the Boltzmann variable rather than the individual Mellin variables. And then the residue comes with some Pochhammer and then some simple polynomial that I will show you in the next slide. But the point here is that this Pochhammer that comes with the label given by the pole, what it does when you put it together with this gamma function that I isolated from the sphere, is essentially splits you these pairs of gamma function in two separate contributions. So it realizes, so crossing is realized, but in a rather non-trivial way, because now you have two separate channels, one which is labeled by plus and one which is labeled by minus, and the channels, they are labeled by Z, but with respect to the P1 plus P2 or P3 plus P4. So what before was some one block fixed by crossing, if you wish, now it becomes two separate channels with plus and minus, in which the details, they're going to depend on this polynomial R, but the overall pole is just fixed by the Boltzmann variable. So in particular, compared to what I was pointing out before, now there is more room to make the function non-trivial. And in fact, when you look at the specific of the R, you see that depends generically on all the variables, but they're still simple, so this is quite doable as a computation. And quite interesting, when you look now at the large P limit of flat space, that in principle is just given by this W3 function here. Let's give you all you get from string theory in flat space. But this reminder function here contribute as well. They are to the limit, but quite remarkably, individually they contribute, but the sum all of them cancel out, which is what you expect, because this should only be the flat space limit, should not be any other contribution. So in conclusion, here we understand the structure and the details of the one loop amplitude, Mellin amplitude at the one loop at alpha prime cube. The OP, which is realized on the space of the block, is kind of orthogonal to Mellin space in the sense that I need to compute the OP prediction, then I need to re-expand and sum in Mellin space. But then when you look at the Mellin amplitude, everything fits nicely. The simple poles and the transcendental function have both font arguments, so somehow they know already from 10D space, the flat space physics, but then the details is given by the reducible polynomial. This reducible polynomial knows about the fact that there is a sphere, and then there are many Kaluza-Klein modes, so they know about the details. Even though some individually they contribute to the flat space limit, then the large P limit works in a remarkable way. So we expect these answers to be generic, and in fact preliminary results confirm this when you look at higher order corrections. Note we still need to fix the ambiguities, and this is something that the bootstrap currently hasn't shown a way to do it consistently. So some just outlook, and I'm going to end. We have looked at the regime in which the charge is just small somehow, but the single particle operators, when you increase the charge to be over the n, becomes a D-brane. On the other hand, the perturbation theory that we're looking at from the point of view of quantum gravity breaks down when this is bigger than 1. So you are not going to see some D-brane 4-point function just by looking at the series. The series needs to be resummed, and then something very non-trivial needs to be happened. Similarly, when you look at the alpha prime correction, this goes as this power here. So again, it's going to break down when you go P to order 1 over alpha, 1 over square root of alpha. What happens next? We don't know. This is an interesting question one should try to ask. Even more dramatically, what happens when the single particle operator is taken to be n squared? Then it's not anymore a single particle, it's just a mixture of multi-particles by construction. So it should be some big state. And don't miss out the talks of Peter on Wednesday. He's going to tell you about something about that. Also, it would be interesting to see how it works at weak coupling, because the anomalous dimensional weak coupling of these two particles operator, they go with lambda over n squared. In fact, they should be finite when you take the large n limit and the large 2 coupling limit. However, here, and so this may be a way to understand what happens with non-geometric gravity. So you split the perturbative computation, which I showed you before as no saddle point in terms of classical physics, but maybe just the two particle contribution to one loop physics disentangling the stringy states that has a saddle point that one can study. And then things might happen in other dimensions. So, and one can think about what happens with analyticity across dimensions. So some formula that we came through, they do have some analyticity in the dimension when you move across dimensions. So it's not just n equal 4 superior mix, but also these theories here on AdS3 times S3, AdS5 times S3, and also this more exotic AdS2 times S2. So can one try to find a uniform formalism that put all this theory together, not just at tree level, but at loop level? These are interesting questions that one might try to ask one might try to solve in the future. So let me end up with these things.
Thanks, Francesco. And we have some time for questions. If there are any.
How do these approaches to the Virasoro-Shapiro in ADS compare to these recent works by Aldai, Hansen, Silva? Is there any way they talk to each other?
I think what is happening with I think Aldai is trying to do a different expansion, and this is the classical one here in which expand in alpha prime, and is resumming some slices of this. And the point is that, I mean, the two things should be consistent with each other. I'm sure they're consistent with each other, even though the details have not been worked out. But the point is that even when you take the large P limit, so suppose you take the large P limit, you devise a limit in which you forget about the completion, and then the resummation of that is just the Virasoro-Shapiro amplitude with Boltzmann variable. And there, of course, how we are going to interpret those poles from the point of view of the strings of the AdS5 times S5 theories that has poles of some stringy states. But that's more complicated because to devise this limit here, I need to throw out the completion. And this is important because when you resum it, the completion is going to matter. So in particular, this data is just fixed by a 2-point particle CFT data, not by stringy states. So the stringy states are going to be some states which in this regime here, which somehow affect the result, but they are not precisely this one I'm discussing here. So everything I'm discussing here has to do with 2-particle OP data. So I think what Fernando is trying to do is to resum this function in a different dimension so that he can also explore the poles in a non-perturbative Mellin amplitude in which the pole is looking at is a stringy state.
Can you go to the formula that you showed at some point with a weak coupling result in Mellin space? I had never seen that expression.
Yeah, you have seen it.
So, and this is one loop, right?
Yeah, this is one loop. For any P1, P2, P3, P4, it takes this form here. So it's essentially a box. Then, if this, yeah, you know that if you're just doing 2, 2, 2, 2, then it's just a box with S is little s, T is little t, not this bold font. So let's remember that the bold font guys are the sum of the S for the conformal plus the S for the sphere, similarly for T. So here, the gamma function, they are function of the bold font.
And at 2 loops, there is a similar expression?
So 2 loops, one for the double box, for the double box I think there is, but then the point is what the box square is doing with respect to Mellin space. So I think here for this formula there are 2 things, as I was trying to say in the 2 kind of question you could ask. So this formula is dominated by Konishi, if you think about it, because it's just a covariantization of the box, and the box starts at twist 2 with the anomalous dimension of Konishi. So in this covariantize that structure. But if you try to disentangle the stringy states in this formula from the 2-particle data, then maybe the 2-particle correlator that contributes to this is again of this form here. and not of this form. And then one has to understand what happens with the box square when you got to loop, which is also the same kind of issue in the supergravity limit, but at 2 loops. The box square doesn't really fit to, as far as I can tell you, with this kind of Mellin transform here. So there are some shift by 1/2 which don't fit with this. So it would be
what I had in mind was is it fair to say that there's also some emergence of tanh symmetry in that last formula because only these bold-face variables appear inside the gamma functions? And is it related to this tanh symmetry that Simon and Frank saw at weak coupling?
I think it should be the same as they have at weak coupling for the at 1 loop, just written in this formalism. Yeah. Yeah. So these are covered. So as I said, 2, 2, 2, 2, we just have will not have this part here. We just have the usual UMB cross ratios. But then when you take P1, P2, P3, P4, then you get this. So somehow there is no Mellin. The Mellin amplitude here is again some type of gamma function if you want to extract this. And that's why it has no saddle point. But
Can you comment on 1 loop AdS diagrams with more general matter content? So if I consider, let's say, external states to be massless, but I want to have a 1 loop massive box in AdS, which of this technology will work, and do you think it's doable? I understand you
to promote that to so the massive box from flat space, you want to promote it to AdS5 and AdS5?
No. Well, more generally, say, like we have in flat space, pretty complete understanding of 1 loop diagrams.
Yeah.
For any external states, any massive matter.
Yeah.
Can we have something like this in AdS? So let's see.
Yeah, I don't know. I never thought about that. I can think.
For example, yeah, in flat space, this unitarity methods.
Yeah. Yeah, I don't know an example. I should think about it. Yeah.
Any other questions? Nikolai, is any action on Zoom? Well, let's then. Thanks, Francesco, again.